Hello, so let's take a closer look at the 1,2 electrophilic addition reaction that we know for alkenes, specifically the hydrogen halide reactions that we had looked at in chapter 7. So the electrophilic addition reactions were first studied by Vladimir Makovnikov, and he quickly realized that the reaction was regiospecific with unsymmetrical alkenes. That meaning that through the double bond, we don't have any symmetry. So when we add that hydrogen halide, we specifically get the hydrogen to add to the carbon which currently has more hydrogen, and the non-hydrogen atom, the halogen, adds to the side which has less hydrogen, the side which is more substituted. We can see that in the examples here. We have 0 hydrogens at this carbon, but 1 hydrogen at this carbon. So that's the carbon that gets the hydrogen, and the more substituted side gets the bromine. Likewise with this second example, we have got 1 hydrogen at this carbon as we make up its octet, but 2 hydrogens at this carbon, and so that's the carbon which gets the hydrogen, and the other side, the more substituted side, because it has 2 carbon neighbours, while this carbon just has 1 carbon neighbour. The more substituted side again gets a halogen, and then in a third example, 0 hydrogens attached to this carbon, but 1 hydrogen attached to this carbon, so that's the side that gets the hydrogen. So it gives us our first rule that the rich get richer in hydrogen. Now the reaction itself is a 2-step reaction, and the first step produces the high energy carbocation, that pi bond opening up, grabbing the hydrogen first, adding to the side which is already richer in hydrogen, and so creating a carbocation which is more substituted. 1, 2, 3 tertiary carbocation in this case, 1, 2 secondary carbocation in this case, and 1, 2, 3 a tertiary carbocation in this last case. That gives us our second rule. The carbocation produced is the more substituted. Tertiary compared to the secondary which might have been produced. Secondary compared to the primary. Tertiary compared to the secondary which otherwise would have been produced. And we can see why the more substituted carbocation is preferred. It's because it's lower in energy as we'll look at the transition and that intermediate point, and it's therefore more stable. More substituted carbocations are more stable. But why is it more stable? Well, there's 2 factors at play here. The first one is the inductive effect. That carbon with the carbocation charge and an incomplete octet is formally positively charged and electron hungry, and it draws the electrons in those carbon-to-carbon bonds closer to it to offset that instability and take the edge off the charge. So a primary carbocation would only have 1 neighbouring carbon, and therefore 1 carbon-to-carbon bond that it could draw electrons from, while a secondary carbocation would be more stable, being able to draw electrons from 2 carbon-to-carbon bonds. And of course a tertiary carbocation would be the most stable because it can draw electrons towards it from 3 carbon-to-carbon bonds. That's the most important factor, but there's also a contributing effect from hyperconjugation. Again, looking at that carbocation atom, of course it's sp2 hybridized, trigonoplanar, with an empty atomic orbital above and below the plane, and the bonding electrons in those nearby carbon to hydrogen bonds, those electrons in the orbital overlap slightly with the empty atomic orbital of the carbocation atom. And that helps create stability, as there's a slight sharing of those electrons within the empty atomic orbital. And so the more substituted the carbocation is, the greater the hyperconjugation effect. So let's put this together, because these two ideas so far are actually connected. That is that the unsymmetrical alkenes produce more substituted carbocations, and the more highly substituted carbocations are the more stable ones. If we look at the overall reaction for the hydrogen halide addition to the unsymmetrical alkene, it happens in two steps. We've got that transition energy in the first step and the transition energy for the second step, and that little lull in between, that's our intermediate, our carbocation. So let's split this reaction into two and look at the two steps as if they were two separate reactions. So here's our first step, which is endergonic in nature, and our second step, which is exergonic in nature. And looking at the energy of the transition compared to the product or reactant, which of course really is just the carbocation intermediate. Notice that the energy of the transition to this product, the energy is more similar to the energy of the product than it is to the energy of the initial reactants. Likewise, in the second step, the energy of the transition is much closer, much more similar to the energy of the reactant rather than the energy of the product. Energy-wise, they're more similar, because the product and reactant in these two halves of the same reaction is the carbocation intermediate. So if they're similar in energy, Hammond postulated that they were similar structurally to each other, and that's important. Similar energetically, so similar to each other structurally. Why is this important? Well, the structure of the transition state should closely resemble the structure of the carbocation itself. And of course, stabilizing the carbocation should stabilize the transition to that carbocation intermediate. And we have seen that becoming more substituted makes a more stable carbocation, and that will therefore stabilize the transition to that carbocation and make for a faster reaction. So let's look at some examples of 1,2 electrophilic additions. Remember, it's in two steps. Our first step is the formation of the carbocation. And as we look at our two reactant molecules, we have got the nucleophile in the shape of the alkene. That nucleus lever is electron enriched. This is the molecule which is going to instigate the reaction. And our electrophile is a hydrogen bromide, because of this polar covalent hydrogen to bromine bond, with the electrons being drawn away from the hydrogen atom, making it electron deficient, making it an electrophile, an electron lover or acceptor. So that pi bond opens up and the electrons reach out and grab the hydrogen. Of course, a hydrogen can only have a duet like helium, and so as these pi electrons make this new bond, the existing bond has to pop and the electrons retreat to the more electronegative bromine. And so this produces a carbocation, which is a tertiary carbocation, 1, 2, 3 carbon neighbours, which help the stability through the inductive effect. And it's the carbon on the other end, the carbon which had more hydrogen to begin with, which gets the hydrogen from the hydrogen bromide. the rich get richer. So we're ready for our second step, but now the roles of the nucleophile and electrophile have been reversed. Now it's a electron-enriched and negatively charged bromide ion, which is a nucleophile, the instigator for the next step, and a carbocation with a carbon, which is electron deficient, being the electron lover, the electron acceptor, and we make that new chemical bond between the bromine and the carbon. Remember, our arrows show us where the electrons come from and where the electrons go to as chemical bonds form or chemical bonds break. And we form our final product, the 1,2 electrophilic addition product, with the hydrogen adding to the more hydrogen-rich side, and the bromine adding to the more substituted side. Let's look at one more, the third of our original examples. Again, the reaction is in two steps, and the first step is the attack of the alkene, our nucleophile, attacking the hydrogen chloride, our electrophile. That pi bond opening up, stretching out from the side which has more hydrogen, picking up that hydrogen, or being Markovnikov's rule, and so the existing hydrogen to chlorine bond has to pop and the electrons retreat back to the more electronegative chlorine. We produce that carbocation intermediate. Again, a tertiary carbocation because it has 1, 2, 3 carbon neighbours, which make it more stable through the inductive effect. A second step again with the carbocation. It's now the electrophile, or the chloride is the nucleophile. And so we use a pair of electrons on the chloride to make that new chemical bond to the electron deficient carbon, and we produce a chlorinated product. First step is always the slower of the two steps because we're producing that high energy carbocation intermediate, and it's therefore the rate determining step. While the second step, making a low energy product, more stable product, is a relatively fast step.